Hello, I'm Michael Sidneys, and along with Megan Ross, we will be presenting our senior design project where we did high altitude ballooning, carbon dioxide altitudinal mapping. The greenhouse effect is the leading scientific theory of atmospheric warming. It is currently unknown how the different sources of greenhouse gases populate our atmosphere. By determining how these gases, in particular carbon dioxide, exist in the atmosphere with respect to altitude, we can better determine the effects of different sources on the atmosphere and therefore on our climate. There are several project goals that we have in order to address the identified problem. The first goal is to create an embedded system that's capable of continuously sampling carbon dioxide concentrations in our atmosphere. The second goal is to implement a ballooning system that's safely able to ascend above 100,000 feet. The final goal is to establish a network connection between the payload and the ground station. You can think of this like a long-range Wi-Fi network between our ground station and between the payload that's up in the air. The table at the bottom left of the poster outlines the various functional requirements and design constraints that were formulated using the project goals as an outline. These requirements reflect items such as FAA requirements, sensing goals, and transmission rates. Figure 2 discusses in detail each of the subsystems and how they interact with each other. On the bottom left of the diagram is the ground station. Over towards the right-hand side is the payload. Each subsystems and their interactions are color-coded according to the legend provided. Let's begin by discussing the payload on the right-hand side of the figure. In blue at the top is the cut-down system, which is required by the FAA to terminate flight remotely at their request. Underneath that in green is the tracking system. For this tracking, we use an Iridium GPS service, which is represented in the top left, and it's basically a satellite tracking device that gives us the coordinates of the payload in X, Y, and Z. We use this tracking to orient the antenna system towards the payload. Underneath that is the network system, which allows for two-way communication between the ground station and the payload. Shown in red is the onboard computing unit. The group chose to use a Raspberry Pi 4B, which integrates with the CO2 sensing system shown below in yellow, to process and send the recorded data over the Just Message communication network. Lastly, there's the power system shown in pink, and this mainly represents the onboard batteries. Now let's discuss the ground station in the bottom left. This consists of a large tripod with a movable antenna system on top. Connected to this, shown in red, is a ground station laptop which helps to establish the network connection and auto-orient the movable antenna system so that it's always pointed at the payload. A LAN connection is a connection between computers to link devices, and this is discussed in detail below. Benefits of this system include live data transfer as well as remote control of the Raspberry Pi from the ground station. In order for the dish to always point at the payload, the computer uses the GPS coordinates of the ground station along with the GPS coordinates of the payload to calculate the direction that the antenna needs to point and send control signals to the servos to auto-orient the antenna towards the payload. Initial results from our system can be seen in Figure 4, where you can see the data from the various sensors being received by the ground station.
The next system that we will be discussing is the sensing system that was designed around a few key requirements. First, we wanted a sufficient range of detection, roughly 2 to 2,000 parts per million of CO2. Next, we have to have a densely sampled mapping, so we need a frequent signal update for the sensor. And finally, we need the sensor to easily interface with the computational system we have in place. These and other system requirements led us to select the T6613F CO2 sensor from Telair. For the mechanical portion of this project, we had to consider multiple factors during payload design. For stability, we set our heaviest components towards the bottom. We also had to ensure that the payload met all FAA regulations of surface area and weight so that it was legal for us to launch. The initial SolidWorks design and then our finished payload connected to the balloon are shown in the images on the right. The full systems test was conducted by connecting the payload to the balloon and tethering the whole system to the ground, allowing for a controlled balloon ascension up to around 200 meters. This test, which can be seen in the image on the right, verifies that all systems worked flawlessly as the ground station dish continuously auto-oriented towards the balloon throughout the flight, and data was constantly downlinked to the ground station. The collected CO2 and altitude data from the tethered launch was analyzed and graphed versus time in MATLAB. The balloon ascended to a max height of about 208 meters right after time, 1600 hours and 20 minutes. At the same time, there was a notable drop in CO2 concentration. This corresponds to what we expected to happen and verifies the success of our project. Lastly, we also had some space on the payload, so our group decided to put a 360 4K camera on our payload because who wouldn't want to see a 360 video of space during the launch? The video from the tethered launch is shown to the right. And this concludes our poster. Thank you all so much for listening.